In this lesson, we're going to take a look at electric potential, which is named a little bit weird. It's like electric potential energy, but it's not quite. And in order to help us understand electric potential a little better, first we're going to start with gravity and gravitational potential energy. So remember, gravity has potential energy or causes potential energy because we put something in a gravitational field and gravity wants to pull it down. So if, let's say, this is ground level, I could have a cliff that's this high or another cliff that's this high. Now, clearly, if I put the same rock here versus here, the one that's higher gets to fall further and it has more gravitational potential energy. This is MGH, right? Well, this gravitational potential energy exists because there's a gravitational field that's pulling this rock to the ground. Electric potential energy exists for a different reason, but a very similar reason. If we have an area that has lots of positive charge and another area that has lots of negative charge, then there is an electric field that, remember, starts on positive and goes towards negative. The electric field is this way, just like the magnetic field over here, or not magnetic, sorry, gravitational field over here is also this way. So here, this rock wants to fall because gravity's pulling on it. Here, this rock wants to fall because gravity's pulling on it. But because this height is lower, this gravitational potential energy is less. If we had a smaller separation of charge, so these were closer together, there would be a smaller potential difference between them. And so here we have a higher electric potential energy versus a lower electric potential energy for the same charge, right? If I had the same charge in both of these places and it's a positive charge, then that positive charge wants to move. And since this distance is greater, it can fall further, if you will, and so it has more energy there, just like this rock can fall further and it has more energy there. But this gets a little bit weird if we start looking at different sized rocks. So if this is a 5 kilogram rock, but this over here is a 30 kilogram rock, now it's harder to say which one of these has more potential energy, because this one can fall further because it's higher, so it will be going faster when it smashes into the ground. This one won't be going as fast, but it has more mass, and so its potential energy depends not only on gravity and height and mass, or not only on gravity and height, but also mass. Over here, the same thing happens with electric charge. The energy of an electric charge in an electric field depends not only on the field that it's in, but also on the size of the charge. If I have a really big positive charge over here, that thing might have more potential energy than a smaller positive charge over here. And this one definitely has more potential energy than this one right here that has less charge. And so with electric potential energy, instead of actually talking about the full amount of energy of the charge, we talk about its electric potential. So potential versus potential energy. If we wanted to know the potential energy of this, we would need to know the field strength and the charge. If we want to know just the potential, we just need to know the field strength, really. And so electric potential is the energy per unit charge. Energy per charge. And so instead of telling me how much electric potential energy this thing has, or how much electric potential energy this thing has, or how much electric potential energy this thing has, instead it tells me the potential difference between these two places, and then the potential energy can be calculated simply by knowing the charge. So potential difference is sort of like GH without the M. Right? If I take the GH and multiply it by the M, I know how much potential energy I have. So if this thing is 2 meters high, and it's also, on Earth, so 9.8, this thing has 19.6 joules of energy for every kilogram of matter we raise that high. This thing, if it's 4 meters high, then it would have, times 9.8, 39.2 joules of energy for every kilogram of matter that we raise that high. If the difference in electric potential energy between these two things is, say, 4 joules for every coulomb of charge that we separate, that means 1 coulomb of charge would gain 4 joules of energy as it moved through that field. It has 4 joules of potential energy up here at the top. This joule per coulomb, that's what we call that would be 4 volts. And so a joule per coulomb is a volt. Voltage describes electric potential. And so what that allows us to do is talk about the potential difference between these two places, not because of the charge that's in there, but simply because of the field. And so if I know the charge, remember we usually give charge the symbol Q, and I know the difference in these two places, the potential difference there, then I can figure out the electric potential energy. And so voltage is equal to energy over charge, or energy is equal to the electric potential difference, voltage, times the charge. So this might be a 4-volt difference because it's not as separated as over here. This one might be closer to a 9-volt difference. And so this little charge, if it's 1 coulomb of charge, it would have 9 times 1 is 9 joules of energy. But if I have a 4 coulomb charge over here, and it's 4 volts of difference, 4 times 4 is 16 joules of energy. And so electric potential difference is energy per unit charge, and it sort of is describing how far a charge can fall through an electric field, so how much potential energy any charge would have in that field.